When we talk about adding, subtracting, and multiplying, we're going to leave the last one, which is division of polynomials, for tomorrow. We'll start looking at that one. That's the most difficult of the four. But basically, polynomials, we can add and subtract them just like we could with regular numbers before. So, for example, if we add, subtract vertically, like just think about back to elementary school. Like if I give you the numbers 356 and 27 and asked you to add them, you'd start with the ones column and say 6 plus 7 equals 13, and you'd put a 1 up top here. And you'd say 1 plus 5 is 6, plus 2 more is 8. And then you would just have a 3 that comes down from the hundreds column. So you get 383. The exact same thing happens when we add and subtract polynomials. So with polynomials, we'll want to start with this equation as our top equation and say 2x cubed minus 5x squared plus 3x minus 9. And then our bottom equation, x cubed plus 6x squared plus 11. And what we'll notice is there's a missing value right here. And what we can do there is we can just say plus 0x. And I'm going to do that because this is basically a placeholder. But when I'm adding these things, it's just like if I had 306, the 0 would be a placeholder. So that's exactly what I'm going to be doing here too. And I just line them up vertically, so notice my x cubes are above my other x cubes. And then on the left side, I have -9 and positive 11. Those added together gives me a positive 2. I have 3x plus 0x gives me a 3x, 3 plus 0. -5 plus 6, so that gives me a positive 1x squared. And I have 2x cubed plus 1x cubed. That gets me 3x cubed. That's what this problem would look like adding vertically. Okay. So that's vertical addition of polynomials. That's what it will look like. All right. Just another quick reminder of what we talked about last week was end behavior. So while I'm looking at this real quick, I can see to identify the end behavior, I got to say, hey, look, it's an odd degree polynomial, okay? And it's a positive leading coefficient. The leading coefficient happens to be the number 3. All right. So odd degree, positive leading coefficient. On the left side, it's starting in a negative direction, and on the right side, it's going to a positive direction. All right. So as x goes to the left, which is negative infinity, y goes to negative infinity as well. And then as x goes to the right, which is positive infinity, y goes up, which is positive infinity as well. That's how end behavior works. I can identify that without even graphing it. But if I needed to graph it and look at it visually, that's perfectly fine too. All right. Okay, so the other type of addition we could do is adding horizontally. So that's where we'd say 3y cubed minus 2y squared minus 7y. I'm going to put that all in parentheses, and then I'm going to add it to -4y squared plus 2y minus 5. And basically, to get rid of the parentheses, I would kind of distribute this positive sign, which isn't going to change any of the signs, but that's important when there's a negative if we're doing subtraction, because that will change the signs. But I can write this whole thing out, and now I'm just going to combine like terms. Right here I see a 3y cubed, and that's the only 3y cubed I see. So 3y cubed. Next I see a -2y squared and a -4y squared. So that becomes -6y squared. Next line I see a -7y and a positive 2y. -7 plus 2 is -5y. And then last I see a -5. So that's just going to be -5. And that's adding horizontally. Personally, I prefer adding vertically. I think it's easier for me to line up the values because, again, I'm just lining them up. I want the cubes lined up above the cubes. I want the squareds lined up above the squareds. The x to the first powers above the x to the first powers. And then the constant terms above the constant terms. There's no x's there. Okay, I think that's a little easier for adding vertically. All right. And again, this problem, just like before, and behavior, I can see a third power there, and I can see a positive 3 leading coefficient. So this is another one, odd degree polynomial, so it's going to be going in opposite directions for end behavior from left to right. On the left side, as x goes to negative infinity, it's going to be going down, and on the right side, as x goes to positive infinity, it's going to be going up. It trends positive because I have a positive leading coefficient from left to right. All right. Okay, next thing, subtraction of polynomials, vertical subtraction. So this one's going to be same idea, 3x squared plus 2, or 3x cubed plus 2x squared minus x plus 7. And I'm going to do minus 8x cubed minus x squared minus 5x plus 1. The big important thing I have to do with subtraction is I have to distribute this negative. It's going to change all of the signs. Most common mistakes students make on subtraction of polynomials. Distribute and change all of the signs. Okay. And what that means is when I distribute this, I'm going to get a negative 8x cubed plus x squared plus 5x minus 1.
Wait, isn't it actually the other way around?
What do you mean?
That you're subtracting 3x squared plus 2x squared.
Yes, you're right. I did do that backwards. Thank you. We'll fix that.
Okay.
So yeah, we're going to subtract that from the other one. Yes, the way I wrote it down. Anyway, but the big thing is that we want to make sure we distribute the negative sign. So we'll fix that. Minus 5x plus 1. And then 3x cubed plus 2x squared minus x plus 7. Distribute that negative, so I'm going to get negative 3x cubed minus 2x squared plus x minus 7. Very important to distribute that negative sign, otherwise I will get this problem wrong. And when I distribute that, I'm going to have that negative 3x cubed minus 2x squared plus x minus 7. And again, think about that if I were doing a subtraction problem over here that was like 482 minus 305. All right. I'm not doing 2 plus 5 over here. I'm doing 2 minus 5. I'm technically like distributing that negative to every single line, but I've already know how to do that in those old methods. All right, so that's really important when you're thinking about these problems. I do 12, and then I would get a 1 column over. I get 12 minus 5. I get 7 minus 0, 4 minus 3. But again, I know that I'm doing 7 minus 0, not 7 plus 0. I know I'm doing 4 minus 3. So what happens is a lot of students do the first one subtraction, but then they forget to change the signs on the rest of them. So really important that we're changing all of those signs. So we get 1 minus 7, negative 6. Negative 5 plus 1, negative 4x. Negative 1 minus 2 more, negative 3x squared. And then 8 minus 3, 5x cubed. And that's how we'd end up with this problem if we are distributing vertically. All right? Yes. And great catch there. We do need to say that this is the top term and this is what we're subtracting, okay? Really important that we pay attention to that so we don't make a mistake like I did by setting it up too quickly. All right. All right, another example, horizontal subtraction. The horizontal subtraction, I think, might be a little bit easier for you to, to recognize that you need to distribute. But that's the only advantage, I think, of the horizontal subtraction, is I could see, hey, I need to distribute this negative to all of these terms. It might make that a little easier to spot. But otherwise, you're still combining like terms on the next step, and I think that can be a little bit tricky to catch that. So we're going to do plus z minus 3. Okay, so negative 5z squared plus z minus 3. And then find those like terms. 4z squared, negative 5z squared. That's going to be negative 1z squared. The next like term, positive 9z and positive z, that's actually going to be like an addition problem. It's going to be plus 10z. And then the last part, negative 12 minus 3 more, negative 15. So I think once you distribute that negative, it's almost like an addition problem. Now we're just adding the terms or whatever. But we have to distribute that negative first in order to be successful on these problems. All right. Another quick note, and behavior. Look at this one. Z squared, so it's a degree 2 polynomial, even degree. Leading coefficient, negative, so that's like a negative 1. Negative 1 leading coefficient. It's a degree 2, even degree polynomial. And then I would say, okay, well, this one, it's an even degree, so it's either both are going up or both sides are going down. In this case, as x goes to the left, it's going to be going down. And that's just because it's negative leading coefficient. And as x goes to the right, this is also going down. That's what end behavior looks like. So this is just a reminder of what end behavior looks like from last week. All right. Okay. So we should get good at recognizing those end behaviors with any problem, basically. All right. Multiplication. So we can do multiplication 2 different ways. We can multiply polynomials vertically, and we can multiply polynomials horizontally. But horizontally, I would call the area method, which we've done before, the rectangle area. But we'll take a look at these real quick together. So first, multiplying vertically. I've got this negative 2y squared plus 3y minus 6 times y minus 2. All right. I think vertical multiplication is very difficult, but we're going to show you anyway, just to make sure. We start with, or let's do a numbered example. Say if we did like 86 times 54, we start with the ones column. We say 6 times 4 is 24. And then 4 times 8 is 32, and then we add the 2 up above, that's 34. And that's exactly what we do here with the numbers. We do negative 6 times negative 2, that's positive 12. And then we'll do negative 2 times positive 3y, that's negative 6y. Negative 2 times negative 2y cubed, that's positive, or 2y squared, that's positive 4y squared. That's what we want to do first. Back to our example on the left with numbers, when we're multiplying, we have to do a 0 placeholder. So because we already did the ones column, so now we're moving on to the tens column. So a 0 placeholder. And I'd go 5 times 6 is 30. Put the 3 up top. 5 times 8 is 40, plus 3 is 43. And I'm going to do the exact same thing over here. I'm going to put in a 0 placeholder because we've already done that column, the constants column. Just kind of weird, but that's what we do. And I'm just going to say that's plus 0. And I'm going to start with the y's column. And it's y times -6. And that's -6y. And then y times +3y. Well, y times y is y squared. That's going to be +3y squared. Y times -2y squared. Y squared times y is 2y to the third. All right. And then the last step with multiplication is we have to add. So we say, let's add these two columns. And that's what we're going to do over here as well. So I'd say 4 plus 0 is 4. 4 plus 0 is 4. 3 plus 3 is 6. And then there's just a 4 left. And that's exactly what I do over here as well. I have the 12 plus 0 is 12. -6y minus 6 more y is -12y. 4y squared plus 3y squared, 7y squared. And I have a -2y cubed. That's vertical multiplication. All right. The key for vertical multiplication is you're trying to add up, you're trying to get the columns to line up again, right? Trying to get the y squareds above the y squareds, the y to the firsts above the y to the firsts, the y to the thirds above the y to the thirds, the constant terms above the other constant terms. You're trying to get them all to line up so that way we can just vertically add later. All right, each individual column. That's the idea with the multiplying polynomials vertically and horizontally. Okay, that one's kind of tricky. Personally, I think with addition and subtraction, I prefer the vertical addition and the vertical subtraction, but with the multiplication, I prefer the rectangle area method because that's something we did in AGS2. A lot of us did last year, and that's where we can create the box. And in this case, I'm going to create a, whoops, I'm going to make it a little bit further down. In this case, I can say, let's do 3x squared minus 2x plus 4. And on the other side, x plus 3. It doesn't matter which side, which numbers go on the box, but now I'm just multiplying the terms across. 3x squared times x, that's 3x cubed. X times -2x is -2x squared. X times 4 is positive 4x. 3x squared plus 3, or times positive 3 is 9x squared. 3 times -2x is -6x, and 3 times 4 is 12. And that's our rectangle area problem, right? Now, the only difficult part about this is we still have to combine like terms. So I have to look through it and say, okay, I see a 3x cubed. I don't see any more x cubes, so there's going to be a 3x cubed. And it's either going to be plus or minus on the next line. The next one, squareds, I see a -2x squared and a positive 9x squared. So that's going to be a positive 7x squared. Next one, I see a -6x and a positive 4x, and then there's just going to be a 12 left. So -6x plus 4x is -2x, and then plus 12. All right, that's what these problems would look like if I were doing the rectangle area model. All right, I'm just going to multiply every individual term. Okay, that's a little different than the on the previous problem. So the exponent that was on there was a 2. Made that a little, so it was an x squared, like that. Okay. But that's what makes this problem a little different. I think that's a little easier to work with for me, at least personally, than the vertical multiplication method. Okay. The other type of problem we could see when we're talking about multiplying is multiplying 3 binomials, x minus 5, x plus 1, and x plus 3. That's something else we could see. All right. And what that means is, let's go ahead and draw our first box. We need to do this as two separate boxes. So I can start with, let's say, x minus 5 and x plus 1. It doesn't matter which boxes we choose, but I'm going to need to start one of these methods. And we'll say x times x is x squared, x times negative 5 is negative 5x, x times positive 1 is positive 1x, and 1 times negative 5 is negative 5. Combine my like terms, I see a 1x and a negative 5x, that's going to make it negative 4x. And I end up with x squared minus 4x minus 5. Now that was the result of multiplying these first two terms together. I still need to multiply the third term, so what I can do is I can take this result and I'm going to do another rectangle area method. A second one. It's going to be x squared minus 4x minus 5. And then the second side is going to be x plus 3, because that's what we had up here, the number we haven't multiplied it by yet. And then we go ahead and do our rectangular area model again. So why don't you guys take a minute and see if you can do the rectangular area model multiplication for this problem, and see if you can combine the like terms, and then we'll check our answers in just a second here. So for the second part, x times x is going to be x cubed. X times negative 4 is negative 4x squared. X times negative 5 is negative 5x. 3 times x squared is 3x squared. 3 times 4 is negative 12x. 3 times negative 4x, I should say. And 3 times negative 5 is negative 15. And then the last part, again, just make sure we combine like terms. I see it positive 3x squared and negative 4x squared there. So I had an x cubed minus x squared. And then I had a negative 12x and a negative 5x there. That's going to make it negative 17x. And then finally, minus 15. All right. That covers multiplication. So again, polynomial addition, subtraction, multiplication. I think addition and subtraction are pretty straightforward. We just have to be really good at lining them up vertically so we can make sure the x cubed terms are lined up, the x squared terms, et cetera, et cetera. Multiplication, a little bit trickier, but it should still be somewhat review for us. We're just going to be dealing with higher degree polynomials this year than what we did last year when we were doing the multiplication part. And I prefer, personally, the rectangle area method. If you prefer the multiplying vertically, then by all means use that method. It's entirely up to you. That's why I showed two different methods for each of these three examples today. All right. Are there any questions right now on those problems?